Hello, everybody, to today's IGS seminar. And our first speaker is Elizabeth Case. And Elizabeth Case is a gender fluid glaciologist who just completed their PhD at Columbia University and is now a postdoc at the Institute for Marine and Atmospheric Research at Utrecht University, studying the future of Greenland fern. And they will present on some of their thesis work looking at deglaciation in the Teton Range in Wyoming over the last 70 years. Yeah, welcome, Elizabeth.
Thanks, Falk. Okay, I'm gonna try to share my screen. And then, hold on. There we go. Can everyone, is that the correct?
This looks good.
Screen. Okay, excellent, excellent. Thanks, Falk, for the kind introduction. Yeah, I'm excited to be here to share some work on alpine glaciers today. Most of my work in my PhD and of course my postdoc has looked at continental ice sheets, but this work takes a look at much smaller glaciers in the Teton Range in Wyoming. And this work came about as a part of a Scientists in the Park Fellowship. This is an AmeriCorps fellowship that usually lasts something like 3 to 12 months. And the aim is to embed generally like masters or folks with like science masters with a US national park and with their science team. And this kind of came about, it's sort of been a dream of mine to work in the Tetons since 2015 when I cycled through there and among many other things, 2020 sort of offered this as an opportunity. So I applied for a position in the Tetons, and then the process happened quite quickly. So I was offered the position in March and drove out there in May, where I spent 4 months working in Wyoming and then 2 months remotely. And this was really made possible by support from my PhD advisor and committee, who were very flexible about me taking time off from my PhD, and then of course my funding and my partner. So to start, I'll take you from the Antarctic ice sheet. Well, move north away from where most of my work has taken place and head to sort of the beginning, I guess, of the Western United States in northwest Wyoming, where the Teton Range is tucked just south of Yellowstone and west of the Wind River Range. The Teton Range is a fault block mountain range. It's fairly young, began forming around 10 million years ago, and its geologic context in part leads to this sort of iconic landscape of rising straight out of Jackson Valley, about 6,000 to 7,000 feet above the ground or above the valley floor. And then subsequently, glaciation has really sculpted the range, creating sharp, jagged peaks and numerous cirques and U-shaped valleys that terminate in moraine dam lakes. And you can really see that if we just do a little Google Earth flyby. You can see these large U-shaped valleys, these cirques, these jagged peaks, and we can end here with Middle Teton front and center, and on either side, on the left-hand side is Middle Teton Glacier, and on the right-hand side is Teton Glacier. So the Tetons have between 11 and 14 glaciers, depending on how you look at it. Sort of 11 that have been widely recognized by the park, and then 3 that kind of have been discussed a little bit in the literature and really came out as being fairly similar to these sort of recognized ones. So we've identified 3 new ones in this work. Most of these glaciers are tucked into sort of northwest facing cirques that are surrounded by walls that tower generally hundreds to thousands of feet above the ice surface. This protects them from wind scouring and sun, and supplies them with extra accumulation via avalanching. And this is quite similar to the glaciers that we see remaining in north in Glacier National Park and south in the Rockies. I used a fair number of methods in this work. The goal was really to just get a sense of what how these glaciers have changed since the Little Ice Age. So really this came about because in my work at the national park, A lot of what we were doing was on foot. We were going to the glaciers, we were taking water samples. But it sort of came to be that there's been a lot of work done in the Wind River Range and in Glacier National Park and in the Rockies to the south, but not so much work really focused on the Teton glaciers. And this kind of makes sense because they're like quite small. They're just 4% of sort of the yearly water inflow into the Snake River, which is the primary sort of the large river that this watershed feeds into. But these glaciers are also quite important habitat for some endangered species like the stonefly. So some folks were really interested in how these glaciers were changing, and then of course they're quite an important part of the park themselves in terms of recreation and kind of aesthetics. All right, so the work that I'm going to focus on today, while we do have some in situ and modeling work, I'll just touch on those briefly, but mostly I'm going to be talking about kind of this, the work using airborne and satellite data and imagery. So this includes LiDAR, as well as sort of historic airborne imagery. So we take the historic airborne imagery that isn't yet georectified and using the historic structure from motion package, which was developed by Friedrich Knut at UW, and without whom this work wouldn't be possible. We use photogrammetry to kind of turn this historic imagery into DEMs and georectified orthomosaics. And then from these DEMs and orthomosaics, we can both differentiate the DEMs to get change in ice mass, as well as look at the change in visible ice extent. And this will give us kind of a broad timeline, or a relatively long timeline over the extent of the park about how ice is changing. So we can take a look first at the change in visible ice extent. So this is I guess the plot of all the glaciers in the park and how the ice extent is changing over time. It's a little bit hard to see because they're quite small. So we can just look at the beginning and at the end. So some of these glaciers timelines start in 1954 and some in 1967, depending on when they show up and sort of first show up in imagery. And we can also look at the total glaciated area and how that's changing in the time period between which all the glaciers are measured. And really what you can take away is that most of the glaciers in the park have lost at least 50% of their visible ice, with kind of the notable exception of falling ice and Teton Glacier. And I'll talk about those a little bit later. In order to extend our timeline a little bit, we can look back to little ice signs of how far the ice extended at their maximum during the Little Ice Age. So this is looking for terminal and lateral moraines as well as trim lines, and these signals are quite apparent for some in the park and not so present for others where the moraines have been washed away on like steep slopes, for example. And there's a little bit of historic area, like truly historic imagery that we can use to kind of corroborate the extent, the sort of likely maximum extent during the Little Ice Age. So this is a picture from the Hayden survey in 1896. And you can see Glacier Peak Glacier in the background here. And then we can kind of like figure out where this image was taken in Google Earth. Go check it out. There you can see just in this like firsthand that the glacier is of course retreated quite a bit, but this also gives us a sense and sort of a corroboration of like how far the ice is extended, so we can really like confirm that the little terminal moraine that we've identified in our LiDAR is the actual Little Ice Age moraine, because there's not really been any dating of Little Ice Age geomorphology in the park. And then additionally, the sort of visible ice extent can give us a sense of sort of these periglacial changes. So here we see Glacier Peak, which is the glacier we just looked at, and we can see this proglacial lake forming in front of it, which is quite interesting. You can see little icebergs calve off, and then over time, as by 2015, the glacier is really retreated pretty much entirely from the lakeshore. So we can also take that historic aerial imagery and use photogrammetry to kind of reconstruct historic DEMs. And then we difference those DEMs to get a sense of the volume change or the surface height change of all of these glaciers. So this is kind of what we came up with here. This data set is definitely a little bit noisy, as you can see, but it sort of is dependent on the quality of the imagery that we have to work with. And at least this can give us kind of a sense of a couple of processes that are going on and allow us to kind of figure out whether what we're seeing in the visible aerial imagery is sort of what's happening with the ice itself. So for one, I don't think this will be news to a lot of folks, but visible ice extent is not necessarily indicative of mass loss, especially in steeply confined glaciers. And this is particularly apparent for falling ice and Teton Glacier, where we see very little change in aerial extent, which is kind of in opposition to the rest of the glaciers in the park. And that's because of the way that these glaciers are kind of embedded in what I like to call like these bathtubs of stone walls. So yeah, of course, when you pull the plug in a bathtub, the area of the water doesn't change, but it's certainly lowering and changing in volume. And that's really what we're seeing here. We're seeing the glaciers really decrease in surface height, but not really change much in aerial extent. And then we can also learn a little bit more. So visible ice extent doesn't always capture the full ice extent. These are really steep and like rugged mountainous terrain. And so oftentimes the aerial imagery is obscured by shadows or sometimes by degree cover. And this is true for East Triple and Middle Teton. The sort of aerial extent is outlined here, and you can see that we're not getting kind of the full story. We're missing a little bit of the glacier. Sometimes also these aerial extents don't, instead of underestimating, they overestimate the glacial ice extent. So we see this for Peterson. This too can depend on kind of how much snowfall there was in the year that we have imagery. And then for some of these glaciers, it turns out that the visible ice is really relic ice and it's fairly superficial. It's not really changing any more than the surrounding landscape. So this is true for ice flow and teepee, which are some of the smallest glaciers in the park. And we don't really see significant, we see sort of definitely like a shrink in visible ice, but we don't really see a significant change in ice volume. We can also use these difference DEMs to take a look at rock glaciers, and this is particularly interesting for some of the entomologists and kind of biologists that I've talked to that work in the park that are looking at, for example, rock glaciers as what they call cold refugia. So these are providing like really cold water during hot summers, and rock glaciers seem to be particularly useful sources for that. So this is just sort of like external to the work that I'm doing, but I would love for someone to take a look at this data set and use it to kind of explore the rock glaciers in the park a little bit more. The great thing about the Tetons is that a lot of these glaciers you can really like hike right to, usually within a day. So it's all very accessible. And then finally, we have aerial and satellite imagery. We have this LiDAR data set that we've used to look at volume change, but we also have in situ measurements at Middle Teton Glacier, which is kind of the park's benchmark glacier. So every year the park does a GNSS survey of the surface height of the ice surface height of Middle Teton. And this is nice. It kind of extends our time series. So the LiDAR survey that we have was in 2014, and that's kind of the end of the volume change that we are able to create from this data set. And then the in situ measurements started in 2015, 2016. So in addition to those surface height surveys, they also go at the beginning or at the, I guess, the end of the accumulation season. At the beginning of the summer season, they usually take snow depth surveys, and they embed some ablation stakes. And from these ablation stakes, we can see how fast the glacier is moving and also how much melt is happening at the surface to kind of corroborate those GNSS measurements. And similar to what we saw for the GPS surveys. At all locations, we see ice loss on the order of 1 to 6 meters during the summer seasons between or within 2019 to 2022. And so we can take these kind of like 3 data sets. We're looking at historic volume change as well as present day volume change, and trying to get a little bit more of the story out of there, continuing this. So the ablation stage, so 1 to 6 meters of surface ice loss. The GNSS surveys show 0.5 meter to 5 meters. These are both within 2016 to 2021, 2022. And then we can look at the surface height change between 1967 and 2014, which is obviously a much larger time. And there we see an average of 5 meters. So you can really get a sense that ice loss is accelerating in the park quite significantly. And we can kind of bring this story all together. So you see that we can plot the aerial change here in green, the volume change in blue, look at how these 2 sort of sources of information either align or don't. But in the end, the story is kind of the same as with all other alpine regions, which is that we're losing our alpine glaciers faster and faster. And to wrap up this talk, that this is it's really hard to be in a place and to see this loss happening in real time. And when I presented those results of the in situ data to one of my coworkers at the park, she literally burst into tears. It was a really emotional moment. There was a lot of ice loss in 2021, and this kind of prompted the creation of this small art booklet that takes those satellite images that we were using to do this DEM differencing and to look at the change in aerial extent, and we put some poetry over the top, and this was published as a zine, and it's been distributed, like 1,000 copies have been distributed. So with that, I'd like to end, and yeah, thanks so much for listening. I'll stick around for questions at the end.
Thank you a lot. Yeah, really nice talk, and also really, yeah, nice to try to communicate the changes that we see in ways which are maybe going above only the scientific spreading. Okay, yeah, so as always we have questions in the end, and so I would just suggest to continue with our next speaker before we come to this. So our next speaker is Clara Henry, and she recently completed her PhD where she investigated ice flow dynamics of Antarctic pinning points at the University of Tübingen and the Max Planck Institute for Meteorology in Germany. And now she has started a postdoc position at Stockholm University, where she's working on numerical methods applied to coastal regions. And today she will talk about a chapter of her PhD project, which is about modeling the 3-dimensional diagnostic anisotropy field of ice rises. Welcome.
All right, thanks, Falk, for the introduction. I'll just share my screen. All right. So as Falk mentioned, today I'm going to speak about a chapter from my PhD thesis. So I'm going to talk about modeling the 3-dimensional diagnostic anisotropy field of an ice rise. This is in collaboration with Carlos Martin and Reinhard Drews at BAS and the University of Tübingen. But I'm also going to talk about some previous work with some other co-authors as well. So what exactly is an ice rise? So an ice rise forms in ice shelves. An ice rise or an ice rumple forms in ice shelves due to an anomalous bed below the ice shelf, which pushes into the ice shelf and causes buttressing or a sort of back force on the ice shelf and in turn also in the ice sheet. And this then has an influence on the grounding line position. So throughout my talk, I'm going to speak about pinning points as a general term for ice rises and ice rumples. And so where do you actually find ice rises and ice rumples? They can be found in each ice shelf around the coast of Antarctica. And so in blue, you see the outline of the ice rises, and in red, you see the outline of the ice rumples. So there are roughly 170 ice rises in Antarctica and over 500 ice rumples. And as an example, a study by Ranja-Rees et al., they looked into the continental grounding line flux in response to ice shelf thinning. And this was seen to be higher in the case of thinning close to pinning points. And then in a very recent paper, it was also shown that between 2000 and 2022, 37% of pinning points reduced in size. And so in one chapter of my PhD thesis, we looked into the hysteresis of ice rises in response to sea level variation. So what we did was we took a steady state ice rise, so we modeled it, and then we increased and decreased the sea level and found that these features respond with hysteresis in response to that perturbation. So not only is it important to understand the influence of pinning points within ice sheet dynamics, ice rises and ice rumples are also very useful as a natural laboratory. This is because they have all sorts of different types of flow regime. So ice rises quite often have this ridge divide, and then you have this flank flow, and then you also have the transition from grounded to floating ice at the grounding line. And so there's quite a lot of previous work that looked into like the ice flow physics. So looking into Glenn's flow law exponent, into basal sliding and anisotropy, which is what I'm going to talk about today. And so to discuss my research question, so we were interested in looking at what the modeled anisotropy field, or the dependence of the modeled anisotropy field on the model parameters. And this is sort of motivated by advances in data acquisition and a sort of need for a modeling framework to make comparisons with. So what exactly is anisotropy? So on the right-hand side, you see that ice crystals have this hexagonal crystal lattice structure. And then we define this vector that's perpendicular to these hexagons called the c-axis. And in the model that we're using, so we're using Elmer ice, we model the anisotropy by using a crystal orientation tensor evolution equation. And so the evolution of the crystal orientation tensor is dependent on the spin of the ice and is also dependent on the strain rate and the deviatoric stress. In this study, what we've done is we've taken parameter combinations from 4 previous studies and run the simulations with those different combinations. So this influences the relative dependence on the strain rate and the deviatoric stress tensors. Okay, so what exactly is a crystal orientation tensor? So what I'm showing you here is an example of some data. So basically a crystal orientation tensor, it describes the spatial distribution of c-axes or the fabric. So what you see on the left-hand side is isotropic ice. So this is a projection from a sphere of c-axes onto a circle. And so the vectors are each represented by a point here. And in the isotropic case, the distribution is quite random. If the c-axes then start to align along an arc or a circle, then we call it a girdle fabric. And if the c-axes kind of point in one direction, then we call it a single maximum. And so from data, you can construct a crystal orientation tensor. And then by calculating the eigenvalues and eigenvectors of that tensor, you can then describe the fabric. So this is just an example of like what a crystal orientation tensor is. Okay, so the type of flow regime influences the fabric type. So what I'm showing you here is a sort of typical pathway for an ice particle, which undergoes different types of flow. So on the left-hand side, you start off with this sort of dome flow or ridge flow. So you have snow falling, turning to ice, and then being compacted from above. And then as it moves into the flanks, it starts to, there starts to be like vertical shearing. And then once it moves into the ice stream or an ice shelf, the flow starts to be dominated by extension, so stretching of the ice. Okay, so what sort of flow or what sort of fabric types do you have in each of these parts of the flow regime? So first, when that snow falls and it turns to ice, the ice is quite isotropic. So the c-axes are kind of randomly oriented. And then under compaction, the c-axes start to point towards the highest force. So they point towards the vertical. So that's what you see here. And then as the ice moves into the flanks and towards the ice shelf, you start to get this girdle fabric. And then in the ice shelves, you can also start to get these like a single maximum forming again. Okay, so how is anisotropy data actually gathered? So you can either gather it with an ice core or using quad polarimetric radar. There's other techniques as well, but I won't go into them. So there's been quite a lot of recent progress in the processing of radar data for this purpose. So this allows the acquisition of two-dimensional data, whereas like ice cores are quite expensive and only give us one-dimensional data. But there are assumptions if you're gathering this data with radar, and one of those assumptions is that one eigenvector of this crystal orientation tensor is vertical. Okay, so the area that we've been studying and modeling is Derval ice rise. It's an Isle-type ice rise in East Antarctica. And so you can see it's surrounded by ice shelf and not connected to the continent. Okay, so as I mentioned, we use Elmer ice to model Derval ice rise. And so in the area encompassing the ice rise, we use a horizontal resolution of 500 meters and a lower resolution elsewhere. What I'm showing you now is the modeled velocity field of the ice rise. So what you can see is that there's quite a clear ridge divide where I've drawn this dashed line, and the velocities in the ice shelf surrounding it are quite a lot higher. Okay, so now moving on to some of the anisotropy results. What I'm showing here is the largest eigenvalue, so lambda 3. And this is again for the different parameter choices. And what we see is that the largest eigenvalue is highest at the divide, which is to be expected. So here, so this is a cross section through the ice rise, through the divide. What we've also explored is the deviation from this assumption that one eigenvector is vertical. So what I'm showing here is the angle between the vertical and the eigenvector corresponding with the largest eigenvalue. So what you see is like in two of the simulations, you have a very low angle. So the assumption holds fairly well, whereas in the other two simulations, you get a bit more of a deviation. And so this is, the assumption mostly holds in simulations with a higher dependence on the strain rate term in this equation. And then what I've also plotted is what's called the Woodcock K value. And this gives us a quantitative metric for the type of fabric that we have. So if we have a higher value, so more blue, then we have more of a girdle fabric. So that's where the c-axes are aligned along a circle or an arc. And if we have sorry, I mixed that up. It's the other way around. So quite low is girdle fabric, so the red zones, and quite high is unidirectional or single maximum fabric. So that's more the blue zones, so here and here. And so looking at these results, we actually suggest that it's quite important to gather data at the ends of the flow divide, so in areas where we have quite high divergence of flow. Okay, and so in conclusion, we found that fabric type differs depending on the parameters chosen. And we've also shown that it would be quite good to gather data in areas of high horizontal divergence so that we can constrain model parameters. And we also show that in some areas, the deviation from the vertical needs to be taken into consideration when using quad polarimetric radar. All right, then, yeah, thank you very much for listening. I'd like to also thank all my co-authors and also mention that, I mean, this is work from my PhD, but now I'm based in Sweden at Stockholm University in the group of Josephine Krona. Yeah, so I look forward to answering questions after the last talk. Thank you.
Yeah, thank you a lot for your nice presentation. And yeah, as Clara said, we will have our last presentation now before we come to the questions. And yeah, so I directly introduce our next speaker, who is Stephanie Olinger, and she is currently the Thomson postdoctoral fellow in geophysics at Stanford University. And she received her PhD from Harvard University in geophysics, where she used seismic data to study ice deformation and fracture. And she's interested in fractures on ice shelves and icy moons, seismology and distributed acoustic sounding, and climate intervention strategies. And yeah, today she will be talking about ice shelf rifting. And welcome, Stephanie.
Hi, everyone. Thanks for the lovely introduction, Falk, and thanks for my folks who spoke earlier and gave some really interesting talks. Today, I'll be sharing a bit about some research I did as a PhD, and then some of the work that I've started here at Stanford. In making the talk, I realized it may be an ambitious amount of content to include in a short talk, so some details may be glossed over as we go, and I'll be happy to get into more detail on simulations and model setups if people desire in questions. So I'll share my screen now and get started. Okay, so I've titled this talk Rifting Across Timescales, Seconds to Decades. So I've, in general, studied the process of ice shelf rifting, which we'll talk a little bit more about in a second. But this is an interesting process because it can span really quite a variety of timescales, all of which might be relevant for ice shelf stability. So we'll look at some work that constrains sort of the fastest timescales we've observed for rifting. And then we'll look at some work that considers what happens to rifts on longer timescales. And as Falk mentioned, I'm a postdoc currently at Stanford University. And all the work that you see here was done in collaboration with Brad Lipovsky and Maureen Denol at University of Washington, and with Eric Dunham and Qingyao Lai at Stanford. So what's the deal with ice shelves? As many of you know, ice shelves are these large floating extensions of the Antarctic ice sheet that surround the continent. They're shown here by all the colored areas, which are coded according to their basal mass loss rate from 1994 to 2010. But why are they actually important? You might say, oh, well, they're floating already, so they displace an equivalent mass of water and therefore have no relevance to sea level rise. Well, most of you know that this is not, in fact, entirely the case. There's a little more nuance. Here's a schematic from Hilmar Gunmanson's 2019 paper. that shows an ice shelf flowing across the grounding line, or the transition point between grounding ice and floating ice. And we can see in the schematic that there's some back stress or some lateral drag that's exerted along the contact area between the ice shelf and its rocky margins. And so if we lose ice shelf mass through either thinning, which is shown in red here, or through calving of icebergs, which can decrease the areal extent of the ice shelf, we've decreased the total contact area along which that side drag is exerted. And what that means is, in considering the force balance of the ice shelf and of the glacier behind it, there's now less force resisting the driving stress that pushes the glacier downslope. And so what that means is, if we shrink an ice shelf, essentially the glaciers behind it speed up. And this is something that we've observed observationally, of course, with the collapse of Larsen ice shelf in the early 2000s. So it's well supported by theory and by observations. So how do ice shelves actually lose mass? There's two primary ways. One is basal melt. Here you can see a high-level schematic of some circumpolar deep water or warm water circulating underneath Pine Island Glacier ice shelf, which is thinning in response. And then there's also iceberg calving, which is the process by which these large fractures create chunks of ice that break off. And you can see here, right, that there was a 50-kilometer or so portion of the margin that now is no longer in contact with shelf ice. This is Ronnie ice shelf, by the way. And there's some observational evidence that suggests that basal melt and iceberg calving make a roughly equivalent contribution to loss of ice shelf buttressing being that tendency of ice shelves to hold back or buttress the Antarctic ice sheet behind them. So iceberg calving is the process we'll focus on today. In particular, we'll think about rifting, which is the fracture process that actually leads to the calving of the largest icebergs, which are referred to as tabular icebergs. Certainly in tidewater and marine terminating glaciers in Greenland, for instance, as well as in Antarctica, there's calving of smaller scale icebergs that happens along the ice front. But the process by which these large, sheet-like chunks of ice break off is this through-cutting fracture process called rifting. There's a rift right here on Pine Island Glacier. This is a lovely animation that was made by Adrian Luckman at Swansea University. And we'll see here a few years of sort of cyclical rift initiation, propagation, and iceberg calving at Pine Island Glacier ice shelf in West Antarctica. So we can see here, right, these rifts open, they propagate, and then they calve icebergs. But it turns out it's actually quite hard to know exactly what's happening there, right? It kind of looks like brittle fracture, right? These look like cracks in glass, for instance, but the time scale over which they happen, again, varies quite a lot. And the closest spaced remotely sensed observations that we have a repeat time of a couple days. And if ice as a viscoelastic material maybe has a Maxwell time of something like 1 day, which is the transitional time scale between more elastic behavior and more viscous behavior, a remotely sensed observation every 3 days actually doesn't allow us to distinguish whether we're observing an elastic or viscous process. So seismology, it turns out, is a helpful tool here because we get continuous in time measurements of the elastic wave emissions from fracture propagation. So that's one of the research tools that I predominantly use to study these types of fractures, because it can allow us to look really while propagation is occurring at what's happening and allow us to constrain the time scale a little bit better. And so again, to return to sort of the concept of this talk, first we'll talk about the rapid dynamics of propagation, and then we'll talk about what happens to rifts as ice shelves thin, which is a process, of course, that can, operate on timescales of decades to centuries. Also, I've hidden the meeting controls and such for my own convenience. So if I begin to egregiously lapse on time, please someone unmute yourself and stop me. So to think about the fast rift propagation dynamics, we'll look at Pine Island Glacier ice shelf, which is an ice shelf in West Antarctica and one of the largest Antarctic contributors to sea level rise currently. So here's some nice imagery from the TerraSAR-X satellite showing one particular large rift in Pine Island Glacier. This was taken in May of 2012. And we'll zoom in on this area in the subsequent plots. The black triangles, by the way, show the location of the 3 seismic sensors that we'll use in analyzing this rift. So between May 8th of 2012, which is shown here, and May 12th or May 11th, what we can see is that this secondary rift here in the shear margin propagates by about 10 kilometers. So you can see the initial position marked in the left figure by a star, and then the final, the new rift area shown in orange here in the right-hand panel. And so already a 3-day time window for 10 kilometers is already quite a remarkable observation in terms of rapid rifting. But we're lucky enough, as I mentioned, to have seismic sensors that were deployed on the ice shelf during this propagation event. So we can look at the elastic wave emissions during that period of time. So what we see, we're looking at vertical velocity seismograms here, is that between the times that the 2 images were taken, it's largely quiet with some small seismic signals. And there's one really big signal that happens on May 9th, which naturally might be a candidate event for the seismic signal generated by the rifting because it's so long in duration and high in amplitude. And so if we zoom in, we see something like this. Again, this is remarkable because it lasts about 2 hours or more with these long period oscillations in which the ice shelf moves up and down. And that it's a really broadband seismic signal. You can see there's tons of high frequencies up front, and then these really long frequencies that follow later. It turns out that we're pretty sure what we're seeing here is essentially flexural gravity waves and flexural gravity wave resonance of the ice shelf that's excited by fracture. So it's the entire ice shelf essentially bobbing up and down like a gong that's been hit by a hammer in response to this fracture opening. And so if we look up front at the very start of the seismic signal and filter to a higher frequency band, before we were looking at periods from around 1,000 seconds to 1 second. Now we're looking at periods from 0.1 second to 1 second. So much higher frequency. What we see is a markedly different seismic signal. There's this gradual increase in amplitude that we'd call it an emergent signal, and then a rapid decay in amplitude. And then it's quiet in this frequency band for the remaining 2 hours. And so if we were to go and plot the particle motion or how the ground is actually moving for these waves, what we'd see is that they're predominantly body waves radiated by fracture. So P waves and S waves, the same way we'd expect from an earthquake. But what's convenient about this is we might say, okay, well, before rapid propagation starts, we don't expect there to be any body wave radiation. And after body wave radiation stops, that means that rapid propagation has stopped as well. So we use the duration of this high frequency signal, which is about 300 seconds, to constrain the duration of the propagation event. And we know that the rift increased in length by about 10.5 kilometers, which allows us to estimate a propagation rate on average of around 35 meters per second. This is remarkable because it's the fastest observation of rift propagation, I think, in the observational record. And I mean, that in and of itself is significant because it shows that rifting actually may not be this cyclical year-long process. It might be able to occur on really rapid timescales and could potentially present a mechanism by which ice shelf geometry and buttressing could rapidly change. But it's interesting to consider why it isn't even faster. Seismic rupture velocities for earthquake faults, for instance, often happen at a high fraction of the shear wave speed in the material, which is thousands of meters per second, but we're 2 orders of magnitude lower than that. But what's different, of course, between an ice shelf and a earthquake fault is that an ice shelf is floating. So we hypothesize that water flow into the rift modulates the rate of propagation. In order to test this hypothesis, what we do is set up a simple, really idealized model of a rift, and I'm not going to get into the details here at all in the interest of time, but essentially we couple the water flow with the conservation of mass of water within the rift, and that relates to the rift stresses because the water pressure of the water within the rift is one of the things that pushes the rift open, and then those stresses are related to the motion of the crack tip. And what we'll do is initiate rifting and let the system evolve until the length increases by the observed amount. And so what we see here for each figure, we'll look at 2 cases. We'll look at the orange case, which I've described as instantaneous. What that means is that the water level within the rift does not change, right? Water is instantaneously supplied into the rift, which is unrealistic. And then the simulation that I described previously, the ocean-coupled simulation, in which water has to flow into the rift at a rate that's physically determined. So for the ocean-coupled simulation, we're able to reproduce the average rate of propagation that we observe quite well. And if you look at the rate of propagation on the left axis for the instantaneous case, what we see is that we approach the Rayleigh wave speed. Here on the left, we're looking at the ratio between the observed propagation rate and the Rayleigh wave speed, which for opening mode fractures is the limiting velocity. So for the instantaneous case, we reach the Rayleigh wave speed quite quickly. But for the ocean-coupled case, we actually stay below 5% of the Rayleigh wave speed. So why is this? What is actually happening? It's elucidated a bit by looking at what happens to the water level, shown in black here, for the ocean-coupled case through time. It turns out that the water level within the rift actually decreases as time passes and as propagation continues. And then once propagation stops, you get the simple harmonic oscillation of the water line, essentially sloshing up and down of the water within the rift. So what actually is happening? It's essentially that water can't flow into the rift quite fast enough to maintain the equilibrium water level. Essentially, right, water has inertia. You can't instantaneously accelerate it. So when you create a pressure gradient by opening the rift, water can't immediately enter that. And so because there's that time lag, essentially, you have waterline depression because water flow can't quite keep up with rift opening. And what that means is the depth integrated, like water pressure stress acting to push the rift open, actually decreases with time, which means that we have this this stabilizing process, essentially, by which instead of continuing to increase in rate, instead of propagating faster and faster, the propagation rate is actually stabilized in some ways by the hydrodynamics. And so sort of the conclusions from this part of the talk, well, it does seem like rifts can propagate through brittle fracture. Even with the hydrodynamics we've described, the time scale here is fast enough that that viscous rheology is not really an accurate description of how the ice has to be deforming. And significantly, we observed that rifts can propagate at rates of at least order of 10 meters per second, but that the precise propagation speed for these cases is controlled by the hydrodynamic coupling. So that's sort of the fast end of rifting. Now we'll talk a little bit about the slow end. I think that I'm taking up my time here quite quickly. So we'll gloss over some details here, but think a little bit about how stress intensity factors, which essentially describe the concentration of stress at a rift, change as the ice shelf that the rift is in thins. So as we saw here earlier, right, ice shelves across Antarctica are thinning due to basal melt. What happens to rifts as ice shelves thin? Are they stabilized or destabilized is the basic question here, right? Does the ice shelf become more likely to crack through rifting or less likely to crack through rifting? So what we're going to do to model this is essentially take a simple model of a ice shelf. And I'll mention this is all elastic modeling, which obviously does neglect the viscous evolution of stresses that happens on long time scales. But we're interested in thinking about what happens to the elastic loading that arises simply from the rift and ice shelf geometry and boundary conditions as the ice shelf gets thinner. And then we're going to vary the rift position and the ice thickness. And then we'll use those modeled displacements from our finite element simulation to estimate the 3D stress intensity factors that arise at the rift. I'm going to gloss over all of these modeling details and happy to answer them in questions if people want, because I think it's going to take up too much time. But we consider several different boundary condition combinations, which I'll show on the next slide. And then briefly from a conceptual perspective, the loading that's relevant here, right, is essentially the membrane stress, which I've denoted sigma here, or the extensional stress that the ice shelf experiences. And then this bending moment that arises due to the depth-dependent nature of the water pressure stress that's acting on the ice front. And so that is felt, the loading is felt here at the ice front and also along the rift walls, which is really quite significant. So there's this bending tendency along the interior walls of the rift. We do some stuff to get the stress intensity factors from the displacements. And again, we can talk about that later if anyone's interested. But the boundary condition cases we consider are strong margins, which is essentially a zero displacement boundary condition along the margins. Weak margins, which is zero normal displacement, but other displacements are allowed, so it's a roller boundary condition. And then this ice tongue configuration, which is the water pressure boundary condition on all sides. We do this for central and marginal rifts. and we'll look at the results for one case, strong central, essentially. And then we also consider these half cases in which there's a strong margin and then a transition in the boundary condition. And we'll consider the half weak case, which is one of the least stable configurations. So I've learned from experience, it's a mistake, of course, to try to show the results plots for so many different simulations. So we'll just look at two that kind of represent different end members, the strongest sort of geometry and the weakest geometry. So for the strong margin case, what we see on the right panel here, this is the maximum stress intensity factor for mode 1, which is the opening mode. It turns out that the mode 1 stress intensity factors for all the simulations are orders of magnitude larger than the other modes. So we'll only look at those results. And on the x-axis is distance from the ice front. So 0 here is at the ice front and 90 is quite close to the grounding line. And so we see that the closer we are to the ice front, the higher the maximum stress intensity factor is. That makes sense. Essentially, we're farther from the zero displacement boundary condition at the grounding line. And then on the left axis, or the left plot here, what we're seeing is the stress intensity factor, mode 1, as a function of depth as the ice shelf thins. And this is done by running the simulation repeatedly for different thicknesses. There's not a time-dependent or dynamic thinning in the simulations at the moment. And so what we can see here is that for the thickest ice shelves, we have negative stress intensity factors in the top half of the ice shelf, which essentially corresponds to the top of the rift wanting to close. And that's due to that bending moment that's exerted along the interior rift wall. But at the base of the ice shelf, the rift wants to be pried open, essentially, by water pressure. As we thin, the slope of this line changes because the bending moment is essentially a function of the ice thickness. And so what's neat here, right, is that the thinner ice shelves have this steeper slope, which means the difference in rift behavior at the surface versus at the base is reduced, essentially. And so what that means is that in thinner ice shelves, we might be more likely to have through-cutting fracture rather than basal fracture. So the style of rifting could change. But in the basal part of the ice shelf, what we see is that stress intensity factor does decrease. So there's this interesting dual-fold role of changing the rift style and also stabilizing the rifts in some ways as we thin. And then finally, we'll look for that half-weak margin case, which you can see the schematic down here. Again, the rift position changes the maximum stress intensity factor. When we're close to the grounding line here, we have quite low stress intensity factors that are negative, so the rift wants to close. But when you get to the transition point in the boundary condition, right, that's where the highest stresses are concentrated. And then that decays back down to a relatively large positive value near the ice front. And again, with thinning, what we see is that that slope changes due to the changing magnitude of the bending moment exerted along the rift walls. But the magnitude of the stress intensity factors at all depths does decrease as the rift gets, the ice shelf gets thinner. So for marginal rifts in these sort of configurations that represent ice shelves kind of like Pine Island Glacier, for instance, before 2015, in which it had this transition in boundary condition. Again, the difference between the stress intensity factor at the surface and the base decreases, and the stress intensity factors at all depths do decrease. So overall, as ice shelves thin, we expect that rifting style might change to favor through-cutting fracture rather than basal crevassing. And that comes from the fact that, again, there aren't these situations in which the top of the rift experiences a really strong closure tendency and the bottom experiences a strong opening tendency. That tendency goes away as we thin, and we're more likely to see stress intensity factors that are closer to each other as a function of depth. And finally, the stresses that arise due to the ice shelf sort of intrinsic loading do decrease with thickness, and that means that they can potentially stabilize rifts. So there's this interesting change in behavior that happens, and also some stabilization of rifts as ice shelves thin. And these are preliminary, and we'll hope to expand this to include a little bit more realistic rheology. But I think that's all I'll say for now, because I'm running up on time here. Thanks everyone for listening. I really appreciate it.
Yeah, thank you for a really interesting presentation. And yeah, especially thank you to all of our speakers today. And yeah, now that everybody is back there, I think we can come to questions. And yeah, are there any questions from the audience? Roger, do you have one?
Yes, I have, and thank you to all three speakers. Enjoyed them all very much. First of two questions, if we have time, is for Elizabeth, and it's a bit tongue in cheek. It's where's it all gone? If the ice has disappeared that much, obviously it went off somewhere as water. So is there any corroborating groundwater level, river flow information that might match to it all?
Yeah, the park has tried to install like just like water speed sensors or like little pressure gauges for about the last 10 years unsuccessfully. Part of the problem is that they can't bring in like battery powered tools to use there. So there's no like really local information near these glaciers. But I mean, it's all basically running down ultimately into the Snake River, and probably quite quickly. So some of it's going to stick around. There's a few like small lakes. There's Jackson Lake and Jenny Lake and other lakes, and the water will stick around there for just a little bit. Those lakes seem to be like cold and silty, and then it'll move straight into the Snake.
Cool, thanks very much. So, looked to be a lot of fun doing that field work.
Okay, Ian, you also have a question?
Oh, yes, a very simple question. Is the volume loss of the different glaciers a function of the surface gradient? Are you getting more loss on flatter glaciers than on steeper glaciers? For Elizabeth, sorry.
Yeah, no, good question. And I haven't thought about it in quite that way. The model that we used that was like pretty basic, but it just used sort of the ice extent and then the slope from the DEMs. So I'd have to take a look at I guess, yeah, the sensitivity of the loss to the slope that was used. I can tell you that just from familiarity with the glaciers, that it doesn't seem like necessarily those that are the steepest are experiencing the most loss, but certainly those that are fairly flat, like Peterson, aren't experiencing much. I think largely though because they don't have much to lose. So it's a little hard with this size of a data set. But yeah, that would be it. Yeah.
Yes, thank you. Have you looked at the shading on different parts of the glaciers then?
Yeah, we've only looked sort of at like at the amount of bathtubing, I suppose, around these glaciers. We definitely do, like Teton is sort of a good example. We see less or we see like quite significant loss at sort of like in the exposed tongue, where it's not really surrounded by steep walls. But it also, for me, is hard to differentiate amount of shading from like accumulation via avalanching, from which we have truly no data at all. So, yeah.
Thank you very much. I think the concept of bathtubbing is quite an interesting one. Thank you.
Okay, I think Roland, you're next with your question.
Thank you. Well, three very different and fascinating talks today. I have a question for Clara. You used Elmer ice for your ice rise simulations.
Yeah, exactly.
Yeah, but I'm, as you didn't mention anything, I'm assuming that was done assuming an isotropic rheology for the ice.
Yeah, so we calculate the velocity with Glenn's flow law, and then using those velocities, we then calculate the anisotropy field. So it's not two-way coupled, so it's just diagnostic.
Sure, yeah. So do you have any plans to explore trying to test out some anisotropic rheologies, feeding back in the results of your fabric evolution?
Yeah, definitely at some point. Yeah. I haven't tested it on complicated geometries yet. I've heard there's instabilities, so that needs to be explored.
Okay, thank you very much.
No worries.
Okay, I think we are running like we're running out of time, but I think Roger, you had another question. Maybe if you want, you can.
Yeah, okay. Just very quickly, thank you. Again, it's for Clara. I'm just wondering if you could hypothesize what you think the seismic anisotropy would be like along the kind of separation line at the crest of the ice rise. And I'm saying that because you may have met Ronan Agnew, our recently finished student who's done seismic work on a BAS profile along the Corf ice rise. And he very sensibly stuck his head in the sand when it came to anisotropy, just dealt with everything else.
Yeah, I spoke to him a bit about temperatures at ice rises, but not anisotropy at all. I have to say I'm not an expert on the observation side. I know some about the radar from the group in Tübingen, but seismics, I'm afraid I can't answer that so well. Yeah. So, but which you were talking about a certain side of the ice rise?
No, Ronan worked on a BAS profile that Alex Brisbane did along the crest of along the presumed kind of dividing line along the crest of Corf, and Ronan kind of hoped anisotropy wasn't going to be a big deal, but I just wondered if you had some insights to make him feel embarrassed about what he'd ignored.
Right, so kind of at the crest or like the ridge divide, I would expect a sort of single maximum once you go deeper into the ice, and then if you move away from the ridge divide a little bit, then you'll have this weak girdle fabric. But I think predominantly you would have like single maximum if the crest is the ridge divide, if that's what you mean.
Sure. Yeah. We shouldn't hang around too long. I know it's past the time now, but yeah, maybe we can meet up in the icebreaker at BAS sometime or whatever, and
yeah, sure.
Follow this up. That's grand. Thank you very much to you and to all three speakers.
Thank you.
Okay. Thank you, everybody. And yeah, with the interest of time, I think we come to an end here. But if you have any further questions, please reach out to our speakers directly. Of course, this also counts for the people watching over YouTube. And with this, thank you, everybody, again, like especially to all the three speakers for three very interesting and great talks. And to introduce next week's meeting, we have a presentation by Kai Oshima, and it will be on a different time zone as he's speaking from Japan. And sorry, I don't have the title ready, but please feel also invited to our talk next week. And thank you again, everybody, and goodbye.